Welcome back, my geometrically minded minions. All right, well, tonight we're going to talk about points of concurrency. Points of concurrency. And I know you're going, currency, what? Money? No, I wish it was, but unfortunately we're not talking about money, although it does sound pretty good. Okay, so first thing, concurrent lines. Since we're going to talk about points of concurrency, let's define a concurrent line. Well, concurrent lines are simply three or more lines, so it's three or more lines that intersect at a common point. That intersect at a common point. Okay, so when we look at that, when they intersect at a common point, when we have three or more lines when they intersect, so we know if we have two lines that intersects two or more other lines, or we have a line that intersects two or more other lines, we call it a transversal. If we have three lines that all have a point in common that all intersect, we say those are concurrent lines. And that place where they intersect, that place that they have in common is called the point of concurrency. Okay, concurrency. All right, that point of concurrency, that is that place where they all intersect, where those lines intersect. All right, so when we look at it, that is called a point of concurrency. That's the point where three or more concurrent lines intersect each other. All right, so since we're looking at that, let's go ahead and let's fill in the blank here. You should have this sheet there, hopefully with your notes. So when we look at this, we're going to name the point of concurrency for each of the following. So first of all, angle bisectors. Angle bisectors. Well, when we look at an angle bisector, the point of concurrency for these is called an end-center. An end-center. So the end-center is the place where the angle bisectors of a triangle intersect. Now, and we know an angle bisector is simply a segment or a line that cuts the angle of a triangle into two congruent parts, into two equal parts. Well, the next one, the medians of a triangle. Well, if the medians of a triangle, that point of concurrency for that is called a centroid. Centroid. Please excuse my spelling tonight. C-E-N-T-R-O-I-D, the centroid. That is where the medians of a triangle. If you draw the three medians of a triangle, and remember, medians are those segments that are drawn from a vertex to a midpoint. So if we draw those segments and connect the midpoint to the vertex, those concurrent lines, they will all intersect at the centroid, okay? If we draw the three angle bisectors, they intersect at the end-center. The three medians intersect at the centroid. Now, if we drew the altitude, remember the altitude is the height. It goes from the vertex to the opposite side, forms a right angle. This one is called the orthocenter. The orthocenter, all right? So the orthocenter. This is where the altitudes, and if you draw the three altitudes of a triangle, they meet at what's called the orthocenter. Now, the last one that we're going to talk about, the last one is the perpendicular bisector. Okay, remember perpendicular bisector, it goes from the midpoint of one side, it's drawn to the opposite side, doesn't have to go through the vertex, goes from the midpoint of one side, forms a right angle. We've constructed plenty of perpendicular bisectors. This one is called the circumcenter. The circumcenter. Okay, so the circumcenter is the centroid, that is the centroid. That is the point of concurrency for perpendicular bisectors of a triangle. All right, so let's look at these things. Complete each of the following statements. The end center is equidistant from the, take a guess, what do you think? The end center is equidistant from the sides of a triangle. It's equidistant from the sides of a triangle. The end center. This is what would happen if we were to put a circle inside of the triangle. The end center would be the center of that circle. It would be the end center. It's called an end center because it's when we put a circle inside. Now the circumcenter is just the opposite. Circumcenter of a triangle is equidistant from the vertices, from the vertexes of a triangle. The circumcenter is if we wanted to turn around and draw a circle around the triangle, and we wanted each vertex of that triangle to be on that circle, the circumcenter would allow us to do that. Now, the centroid is blank of the distance from each vertex to the midpoint of the opposite side. So remember, centroid, it's the one that connects our medians to it connects the medians of our triangle, so our midpoint to the opposite vertex, and it is 2/3 of the distance from the vertex to the midpoint of the opposite side. So it's 2/3. So I guess you could flip it and go, hey, well, where's the other 1/3? Well, that's going to be, if it's the centroid is 2/3 of the distance from the vertex to the midpoint, then you can figure out where the midpoint, the opposite one is, that other 1/3. Now the next one, to inscribe a circle about a triangle, if we want to inscribe a circle, to put a circle inside of a triangle, what are we going to use? We're going to use the in center, okay? So if we want to look at that. To circumscribe a circle about a triangle, so we want to go around a triangle, we're going to use the circumcenter. The circumcenter. So you're starting to see the value of these things when we turn around and we look at them. We can start to see the purpose of each one of these. Now, one other thing I want to add here, when you look at that centroid, because the centroid that connects the medians of a triangle, a unique thing about this one, this is called the balancing point. It is the balancing point. So it's the point at which you turn around and you're able to balance a triangle. If you have some sort of triangular shape, or if you're looking at a kite or something and you want to find that point where you could balance this thing on the edge of a pen, on the edge of a pencil, you would use that centroid. It is that balancing point for it. All right, so now let's go ahead and let's fill in this chart here, right? If the point of concurrency is inside, outside, or on the triangle. So we're going to kind of look at these and get these notes down, and we will practice them more in class tomorrow. So right now, if we're looking at the circumcenter, well, an acute triangle, the circumcenter is going to be found in the interior, on the inside. It's going to be inside a triangle. So a circumcenter is going to be inside of a triangle in an acute triangle. And an obtuse triangle, the point of concurrency, the circumcenter, is going to be found outside of the triangle. Okay, so if we want to be able to, if we've got an obtuse triangle, if we're trying to draw a circle around it, that point of that center of that circle is actually going to be outside of it. Okay, and then if we look at a right triangle, it's actually going to be on the triangle. It's actually going to be on the hypotenuse on a right triangle. So we look at that. So for circumcenter, an acute triangle, the circumcenter is inside. An obtuse triangle, the circumcenter is outside. And in a right triangle, the circumcenter is on the triangle. All right, so the next one, an incenter. Well, an acute triangle, it is inside. It is inside of an acute triangle, the incenter. And if we look at an obtuse triangle, the incenter is inside as well. The incenter is inside. And then finally, if we look at a right triangle, the incenter is inside as well. It is inside. Well, here you go. It's an incenter. So common sense, if you're going to turn around and we're going to take a circle and we're going to draw a circle inside of the triangle, and it's going to touch each of the sides. Well, obviously the center of that has to be inside of a triangle. There's no other place for it. So kind of common sense there. All right, so centroid. Remember, this is the one that's connecting the median to the vertex, the centroid. In an acute triangle, it is going to be inside the centroid. So our medians are going to intersect inside. In an obtuse triangle, it's going to be inside as well. So if we were to turn around, if we're going from midpoint to the opposite vertex, and our centroid on a right triangle, it's going to be inside as well. So it doesn't really matter on those. The centroid, because it's going from midpoint to vertex, obviously those things are all going inside, no other place for them. Now, the orthocenter, this is the one that's turned around and drawn from our vertex. This is our perpendicular bisector, and we're looking at this one. So orthocenter, for an acute triangle, it is on the inside. They're all going to intersect inside. For an obtuse triangle, it is going to intersect outside. They're going to intersect outside. And for an orthocenter, it's actually on the right triangle, and it's on the right triangle, and it's actually at the vertex of the right angle. So We look at that one. If we have a right triangle drawn, this one right here is going to be actually the vertex of that right triangle. Okay, so hopefully this kind of just gives you a little information about these points of concurrency. Like I said, we will play with these more in class. Let you go ahead and construct some of these, but right now the biggest thing is just you understanding, kind of have an idea of what they are, where to expect them to intersect. And if you've got it, great. If you're still a little unsure, go back and rewind this. Like I said, we'll get plenty of diagrams. You'll get plenty of practice on this in class. So sounds great. See you in class tomorrow.